Today, we'll be fully deriving Bohr's equation in one lecture. So, what is Bohr's equation? Well, let's start with the hydrogen atom. The hydrogen atom, as you hopefully know, has one proton and one electron orbiting it. This is a very archaic model, but it's the Bohr model, and we're talking about Bohr's equation, so I'll honor it. So, there's only one electromagnetic interaction that can happen between these two particles. The interaction between the proton and the electron. So, what is that interaction going to look like? Well, the force between the two is dictated by Coulomb's law. It's 1 over 4 pi epsilon naught Q1 Q2 over R squared over hat. Now, such that the negative gradient of potential is equal to the force, which implies that the potential, and remember the divergence of the gradient of the potential is the force. And recall that the gradient of a scalar is a vector, the gradient of a vector is a matrix, so on and so forth. So, what do we get here? Well, because of the way that Fe is acting, we get that U is minus 1 over 4 pi epsilon naught Q1 Q2 over R squared and this is the equation that we got at the end of the day. So, now that we have this, what do we do with it? Well, first we plug in the magnitudes of the two charges. Charge 1 is the proton with magnitude E, and charge 2 is the electron with magnitude negative E, which gives a potential of E squared over R, or E squared over 4 pi epsilon naught times 1 over R. Alright, so that's how we're going to start today. We now have the potential function. And recall that for over the last few lectures, we've been trying to derive the radial Schrodinger equation. You see, we started with the 1D equation. We quickly transferred to the 3D equation, and I said we should use spherical coordinates because of how important spherical coordinates are in real life. And more specifically, how a lot of potentials only depend on radius instead of the other two spherical coordinates. But when you try to convert that to Cartesian, you're going to find it's a function dependent on all three variables. And that doesn't work because then we'll be forced to solve, in most cases, a partial differential equation of three variables instead of being able to use separation of variables to split it into a radial equation, which depends on U, and a theta and phi equation that only depend on a few constants. Now, we already solved the theta and phi equations a while ago, but we still haven't solved the R equation because, just like the time-independent Schrodinger equation from a long time ago, it depends on what potential we pick. But now we've defined a potential. So, what do we do with that? Well, let's write out the radial Schrodinger equation first. We get minus h bar squared over 2m psi r, and remember, this is a function of one variable, radius, which means I'm allowed to write double prime instead of a partial derivative, plus this demonic thing is the centripetal term, and is the reason why nothing good in life comes easy. This would have a minus sign. And this is our potential function. And this is all multiplied by psi r. That's equal to E psi r for some energy level E. Now recall that our potential is e squared, or minus e squared, over 4 pi epsilon naught 1 over r. So now how do we approach this? Well, the first thing we want to do is condense this. It's looking very messy right now. Should that be a plus or a minus? I think it should be a plus. So what happens when we try to condense this equation down? Well, first things first, let's divide both sides by e to get this thing out of the way. We get minus h bar squared over 2me psi r double prime plus h bar squared over 2me L times L plus 1 over R squared minus E squared over 4 pi epsilon naught E 1 over R. And well, why not? Let's just bring this over here. Minus 1 psi R is equal to 0. Okay, so this is the equation so far. Now what I'm going to do is I'm going to substitute in the square root of minus 2me over h bar squared. You see, this guy right here pops up a lot of the time. And you might say, well, isn't this complex? And first of all, we've been dealing with complex stuff this entire series, so should be used to seeing it. But, you know, this is a real function we're dealing with right here. And the thing that we're used to is that E, the energy levels of the hydrogen atom, you'll find they're all negative pretty quickly. I mean, don't you remember minus 13.6 electron volts? Yeah, this is what we're going to derive. And there's a big fat minus sign over there, which means this is always going to be a real number, positive number, in fact. So we choose this to be equal to kappa. That means that minus h bar squared over 2me becomes 1 over kappa squared psi r double prime plus h bar squared, well, this becomes minus 1 over kappa squared, L times L plus 1 over R squared, minus, to substitute in kappa here, we have to be a little bit more careful, and we have to write E in terms of kappa instead. So we square both sides and multiply, which gives us E is equal to kappa squared, H bar squared, over minus 2m. There we go. So now, what happens here? Well, we take this, plug it back in. I don't know why I closed this parenthesis, or paren. I don't really care right now. This becomes 4 pi epsilon naught. This becomes 2m over kappa squared, h bar squared, minus 1 psi r. And that's equal to 0. We have everything in terms of kappa. This should be r. Everything else can go in that blob. So, oh, and this is get a plus now. So, what can we do with this? Well, condensing it all down, at the end of the day, we get plus minus 1 over L times L plus 1 over kappa squared, 1 over R squared, plus me squared over 2 pi epsilon naught kappa squared h bar squared. And in fact, we're just going to isolate 1 kappa here. We're going to let this be equal to rho naught. I mean, it's too ugly to write by itself individually. 1 over kappa r minus 1. Now allow me to introduce a new variable. Rho is equal to kappa r. And no, this is not that scary, it's just r multiplied by a constant. So, what happens now? How many have we used? We still have some space here. So, what happens now? Why is it drifting upward? It's supposed to drift down, gravity and stuff. So, who cares? So, now, can we just try solving this using a simple power series of rho? Well, first let's substitute in rho for everything. So recall that psi r of kappa r, which is psi r of rho, if we take the double derivative, of this with respect to rho is actually going to be 1 over kappa squared multiplied by the derivative with respect to r. So, now that that's over with, what else do we have to talk about? Well, let's try to solve this in the form of some power series. Let's say psi r is equal to the sum from n equals 0 to infinity of a. So, what do we do here? Well, we try plugging this in and we see what happens. So we get 1 over, let's first write out the fully condensed equation. It's looking a lot nicer. Now what we're going to do is try to substitute in this power series. We get 1 over kappa squared, this sum from n equals 0 to infinity, n times n minus 1, rho to the n minus 2, and then what's going on here? Well, you have plus psi r, so we're going to get an rho, I guess, minus L times L plus 1, an rho to the n minus 2, plus rho naught, rho to the n minus 1, minus an rho to the n is equal to 0. This right here. So, what happens now? Well, let's try to add up all of these terms and see what goes on. For n equals 0, we see that there's not just 1, but 2 terms of degree minus 2. That's kind of concerning. Now, can we fix that in any way? Oh, well, actually, there's not 2, there's just 1. In fact, that makes things worse, because if there were 2, they could cancel each other out. But now that there's just 1, and there's no way for it to be 0 other than a0 being 0, which would force all other coefficients to be 0 and give us the trivial solution of psi r equals 0, which is definitely not what we want because it's non-normalizable. That means that, there's no way to get around this, because there's going to be a rho to the minus 2 term. And if we want this power series to be equal to 0, and there's nothing to cancel out the rho to the minus 2 term, we're screwed. So that means we can't use a power series here, at least not directly. So what can we do now? Well, here's what we can do. Let's try looking at the function's asymptotic behavior to see if anything's going wrong near the center of our power series, which we chose to be rho or r is equal to 0. So, we get the equation 1 over kappa squared psi r double prime plus minus L times L plus 1 over rho squared plus rho naught over rho minus 1 psi r is equal to 0. Why with that? So, can we analyze how the solution is going to potentially look near 0 and near infinity? Well, I guess we can try. So what happens? Well, near rho is equal to 0. I need water. Is there water here? So near rho is equal to 0, we get, well, this is going to stay constant, this is going to blow up, but this is going to blow up even faster given it's an inverse quadratic, which means the denominator is going to decrease slower, or sorry, it's going to decrease faster, which means that the numerator is going to increase faster. Still tastes a little like coffee, but it's fine. So around rho is equal to 0, this is going to disappear, this is going to disappear, and as an estimation, this is going to be the only term that stays. So we're going to have that 1 over kappa squared psi r double prime is going to be approximately, or this is going to be equal to, L times L plus 1 over rho squared psi r around rho is equal to 0. Now recall that psi of rho squared is just kappa squared r squared, which allows us to cancel these two out. And so we just get, this is a standard power rule derivative. So we take the ansatz psi r is equal to a r to the k. Hence, a k minus 1 r to the k minus 2 is equal to L times L plus 1 a r to the k minus 2. This cancels out with this, and hence k times k minus 1 has to be equal to L times L plus 1. And there's one solution to this. K is equal to minus L, and there's another solution to this. K is equal to L plus 1. Check these for yourself. So now that we have that, that means there's two solutions to this. AR to the L and AR to the minus L and AR to the L plus 1. Now, when we think about it, anything of the form AR to the minus L is going to spiral off into infinity as you approach 0. And so is its antiderivative, which means we can't use Born's statistical interpretation if psi r acts like this around 0. Which means that that's out of the picture. And this has some very tidy behavior around 0. Starts from 0 and goes up without diverging to infinity. So that means that around 0, this is going to be our only choice. Psi r is approximately going to be equal to AR to the L plus 1 around 0. And of course, you can include a factor of kappa inside the amplitude and rewrite this as a rho to the L plus 1. Where's 5? Now that we've done that, last step, oh yeah. Well, let's try to analyze its behavior around infinity before we move any further. So, around infinity, well, this is going to disappear very fast. This is going to disappear a little slower, but this is going to be the only one staying around at the end. So, well, what happens when this is the only term we consider, as the other two have become too minuscule to account for? Well, we get that around infinity, 1 over kappa squared psi r double prime minus or equal to psi r implies what? Well, it just gives us the standard ansatz psi r is equal to a e to the kr. And now, what happens when we plug that in? Well, we get 1 over kappa squared a k squared e kr is equal to a e kr. So this cancels out with that. And so k is equal to plus minus kappa. But that gives us two solutions once again. So which do we pick? ae to the kappa r, which is ae to the rho, or ae to the minus rho? Well, e to the minus rho is going to stay tidy, and around 0 it's going to be 1, and it's going to slowly, around infinity it's just going to slowly decline, and its integral is going to be finite. But this guy, on the other hand, is going to screw up all of our plans. It's going to diverge extremely quickly, in fact. So we don't want to use it. That means that since the wave function is going to be non-normalizable if it acts like ae to the rho as rho approaches infinity, then we choose that it acts like ae to the minus rho around infinity. Now you might say, well, this guy's integral diverges if you go to minus infinity, and this guy's integral diverges if you go to plus or minus infinity. So what's the resolution? Well, here's the thing. These are just estimations in a specific area. Sure. Here's my red chalk. Sure, you might say that a plus 1 diverges. Sure, you might also say that ae to the minus rho diverges. No, not like that, not like that, not like that. And this is trickier to draw. And that's not important. The only important thing is that around 0, psi acts like this, and then as you approach infinity, it starts acting like ae to the minus rho. But the most pressing issue is what happens in the middle. And to figure that out, we're going to look at psi r overline, which is what happens to psi r when you strip off all the asymptotic behavior. So you multiply it by e to the rho and rho to the minus l minus 1. So this is a bland function except for the middle. But hopefully it's going to be easier to solve the equation. Easier to solve the equation with. Okay. So, number 5. What are we going to do now? Well, we're going to write psi r is equal to the bland function multiplied by the asymptotics that make it interesting. E to the rho, or e to the minus rho, and rho to the l plus 1. So once we do that, now we can take its second derivative, and we can plug that back into the equation that we had right here. So what happens when we do this? We get psi r, well, we can't do the double prime just yet, since this requires repeated application of the product rule. Psi r single prime is going to be equal to psi r overline prime e to the minus rho rho to the l plus 1 plus psi r overline times e to the minus rho rho to the l plus 1. This should have a minus sign since we're taking the derivative of this, plus l plus 1 e to the minus rho rho to the l. Now we factorize that as e to the minus rho rho to the l plus 1 times bland function's derivative plus the bland function multiplied by minus 1 plus l plus 1 over rho. Now, when you take the second derivative, well, with this form, you now use the product rule again. E to the minus rho, minus e to the minus rho, rho to the L plus 1, plus L plus 1, e to the minus rho, rho to the L. Okay, and now you multiply that by this without a derivative, bland function derivative, minus bland function plus times the bland function. Then you add that to this without a derivative multiplied by this with a derivative. Bland function double derivative plus, oh no, another product rule. Bland function derivative, underivative, inner part, plus bland function times derivative of the inner part. And you can factorize this again to simplify it into this once again becomes minus 1 plus L plus 1 over rho multiplied by bland function derivative minus bland function plus L plus 1 over rho bland function and you add that to, well, this disappears because of the factorization, bland function double derivative plus bland function single derivative minus 1 plus L plus 1 over rho plus bland function minus L plus 1 over rho squared. This is the entire thing. Now, what we're going to do is, well, keep working through it, keep persevering through the mess, and we're going to simplify whatever's inside the giant bracket into, well, you have a single psi r or bland function double derivative term. Then, of all the bland function single derivative terms, well, you have one that's minus 1 plus L plus 1 over rho, and another one that's minus 1 plus L plus 1 over rho, which means you have 2 times minus 1 plus L plus 1 over rho. Then, you look at all the terms that just have the bland function, no derivatives. So, you have this term, which is bland function multiplied by minus 1 plus L plus 1 over rho. So that's multiplied by the same factor but outside, which is why I squared it, added to this. Plus minus L plus 1 over rho squared times psi r over line. Okay, and that's about it. So now, that's all of the simplification that we can do. So what happens next? Well, we try to plug this back into the equation from earlier. It's on blackboard number 4. Yeah, this guy right here. So what happens when we do plug it in there? Well, we get 1 over kappa squared. This actually disappears since we're now considering psi r, a double prime, as a function of rho. this becomes e to the minus rho, rho to the L plus 1, psi r, the overline double prime, plus 2 times minus 1 plus L plus 1 over rho, psi r overline prime, plus L plus 1 minus rho over rho squared, plus minus L plus 1 over rho squared, psi r overline, double parenthesis. Okay, so this is all equal to psi r is equal to psi r overline e to the minus rho, rho to the L plus 1. So it becomes L times L plus 1 over rho squared plus rho naught over rho minus 1 times e to the minus rho, rho to the L plus 1 bland function. Now, first of all, we can cancel out these two terms, which allows us to at least break things down a little bit. Okay, now we get psi r over line double prime plus 2 minus 1 plus L plus 1 over rho psi r over line single prime plus L plus 1 minus rho over rho squared plus minus L plus 1 over rho squared psi r over line has to be equal to L times L plus 1 over rho squared plus rho naught over rho minus 1. Things would become so much easier if we actually just multiply both sides by rho squared. So let's do that. And this is also the reason why our power series collapsed a long time ago around rho is equal to 0. So we get rho squared psi r over line double prime plus 2 rho L plus 1 minus rho psi r over line single prime plus this should still have a parent. Well, when this gets multiplied, it just becomes L plus 1 minus rho squared minus L plus 1, and that becomes, on the other side, L times L plus 1, or L squared plus L plus rho naught rho minus rho squared psi r over line. And what happens when we expand this? Well, it becomes L squared plus 1 plus rho squared plus 2L minus 2 rho minus plus 2L minus 2 rho minus 2L rho minus L plus 1. And so this disappears and just becomes L, and hold up. That was, oh, this should have been a minus this whole time. I don't know why I didn't distribute that. So this disappears, and this disappears as well, and that gives you what? This. And now, what else can be canceled out? You can take L squared and cancel it out with L squared, L and cancel it out with L, and actually the rho squared doesn't get to be canceled out, so we can't work with that. But now we also get to divide everything by rho. And we get rho psi r over line double prime plus 2 L plus 1 minus rho psi r overline single prime plus rho minus 2 minus 2L psi r overline is equal to rho naught minus rho psi r overline. And so when you bring this over to this side, you get, or you bring this over to this side, whatever, rho psi r overline double prime plus 2L plus 1 minus rho psi r overline single prime plus, this becomes 2 rho minus 2 minus 2L minus rho naught psi r overline is equal to 0. Oh, no, that's good. So, now that we have all that, the final thing to do is use a power series representation of psi r overline in order to try and solve it. After all, now that we've multiplied it like this, there shouldn't be any leftover terms that we have to force to be equal to 0, right? Okay, well, let's try. Now I'm going to move to the last few boards. We take psi r overline is equal to the sum from k equals 0 to infinity of ak rho to the k. Why don't we use j? I don't know. This right here is the power series that we're going to use for psi r overline. Now what happens when we plug it into this this behemoth? Well, we get the sum from k equals 0 to infinity of j rho aj j minus 1 rho j minus 1 plus 2 times L plus 1 j rho to the j minus 1 minus 2 rho to 2j rho to the j plus 2 rho plus 2 rho to the j plus 1 or 2 aj. Everything here should be multiplied by aj. Plus 2 rho j plus 1 minus 2 rho j minus 2 L rho j minus rho naught rho j is equal to 0. So now we have to figure out what aj is going to have to be for this to work. Can we do the rest of this next time? Okay. So let's first factor just the rho j minus 1 terms. aj j minus 1 plus 2 L plus 1j and that's all of the rho to the j minus 1 terms. Then you have all the rho to the j terms. And the rho to the j terms are, would there even be rho to the j minus 1 terms? All rho to the j terms are minus 2j minus 2 minus rho naught. Plus rho j plus 1. Two, it's just 2. And, okay, this should all be multiplied by aj. Zero. So now, let's do some power series analysis. So let's look at first the term j is equal to k. What do we get? We get rho to the k minus 1 is equal to times k minus 1 plus 2k plus 1 plus rho k minus 2k minus 2 minus rho naught plus 2 rho k plus 1 aj is equal to 0. No, not aj, it shouldn't be aj. No, this is not equal to 0. That gives the trivial solution. Okay, so that's the term, the case term. Now what happens with term k plus 1? Well, we get rho to the k plus 1 plus 2k plus 1 L plus 1 plus rho k plus 1 minus 2 k plus 1 minus 2 minus rho naught plus 2 rho k plus 2 ak. So the rho k terms have to cancel each other out. That's the important thing. So that means that 2k plus 2 plus rho naught has to be equal to, multiply that by, multiply all of this by ak. So this should be ak plus 1. So ak multiplied by this has to be equal to ak plus 1 multiplied by this. And if you factorize this, you'll notice that it's actually k plus 1 multiplied by 2l plus 2 plus k. Wait, no. 2l plus 2 plus k. Yeah. So, since this has to be true, that means ak plus 1 has to be equal to 2k plus 2 plus rho naught divided by k plus 1 times 2l plus 2 plus k, or 2k plus 1, 2l plus 2 plus k, ak. So that's the kind of relation that we want. But you have to realize something here. as k approaches infinity, k plus 1 is going to be much greater than rho naught. And k is also going to be much greater than 2l plus 2. As k approaches infinity, as k approaches infinity, ak plus 1 is going to approximately look like 2 over k plus 2 over k ak. But what happens here? Well, that implies that ak plus 1 will approximately be, as k approaches infinity, 2 to the k over k factorial. And what happens then? Well, it implies that the summation for psi r overline is equal to 2 to the k divided by k factorial multiplied by j to the k, multiplied by rho to the j. That is just e to the rho. Well, e to the 2 rho. And that is the kind of asymptotic behavior that we tried to avoid by multiplying this by e to the minus rho. So, e to the rho. So clearly, if this is approximately e to the 2 rho, then that means that psi r itself is approximately e to the rho. And we can't have that because it means that its integral over the real line doesn't converge by Born's statistical interpretation. So we keep getting non-normalizable functions. What do? Well, the only solution to this is for this series to suddenly terminate. Because since ak plus 1 is always proportional to ak, if suddenly one of these is 0, it totally cuts off the future of anything proportional to it. So that means there must exist some k such that 2 times k plus 1 plus rho naught is equal to 0, which places a really weird restriction on rho naught. But now, what do we remember about rho naught? Well, recall that 7 years ago, where did we define rho naught? Yes, that. So rho naught is equal to me squared over 2 pi epsilon naught kappa h bar squared. So rho naught is equal to me squared over 2 pi epsilon naught kappa h bar squared. So now recall that kappa itself is equal to the square root of minus 2me over h bar squared. So what happens with this? Well, first we rearrange the terms to bring kappa to the head, which gives us kappa is equal to me squared over 2 pi epsilon naught h bar squared times rho naught. Second, we unsubstitute, which gives us minus 2me over h bar squared. Third, we square both sides, which gives us minus 2me over h bar squared is equal to m squared e to the 4th divided by, so this cancels out, 2 pi epsilon naught h bar to the 4th, so this cancels out, rho naught squared. And so we divide both sides by 2. So E is this. But that's not it, because, we just realized that rho naught is this, which gives us minus me to the 4th. Yes, I told you this was going to have a minus sign all along. Divided by 16 pi epsilon naught h bar squared k plus 1 squared. So you can ignore all the fluff, put it in the background, C, and the allowed energy states take the form of C, where C is, some constant, times 1 over k plus 1 squared, where k is an integer. So that's all about Bohr's equation for the hydrogen atom.